to all and welcome to this lecture. We are in module 8, lecture number 2, the extrinsic effects and p-channel transistor. In this lecture, we will see what are the other extrinsic effects we need to take care of when you are modeling the MOS transistor. So, we will discuss about the extrinsic source drain resistances, the effect of temperature, some breakdown phenomena, and I will introduce the p-channel transistor, which is nothing but a flipped polarity transistor in comparison to n-channel transistor. So, these are the learning outcomes of this lecture, which helps you to understand different extrinsic effects which actually alters the performance of your MOSFET. For example, the temperature, the extrinsic source drain resistances, the breakdown phenomena we will see in these lectures. Let us start a lecture with quick recap that in previous lecture we have talked about the effective mobility. We said that the mobility in the MOSFET transistor or in the MOS transistor is actually captured by different scattering phenomena, which is phonon scattering, Coulomb scattering and surface roughness, out of which, considering the strong inversion reason, we model the effective mobility as mu effective was given by mu naught divided by 1 plus a theta cox dash into divided by 2 into epsilon s into Vgs minus Vt plus 2 times of gamma square root of phi naught plus Vsb minus 1 minus 0.5 alpha into Vds. We said that in general when we derive those equations, then the mu effective is dependent on Vds and Vsb, but for the sake of simplicity we ignore the effect of Vds because otherwise the model becomes too complex. To remove this 1 over 2 dependence or square root dependence, we just considered a linear dependence and we concluded this model. We also said that in some instances we need to remove the Vsb dependence, and for a fixed Vsb we plotted the IDVG characteristics. We said that when Vgs increases, then ideally when mu is constant, this linear graph is expected. However, when you include the mu effective, the graph will look like this. So, the current value will get reduced because of mu effective, and if I include the mu effective in IDS, then IDS is no longer square dependent or quadratic dependent, it is approximately equals to Vgs minus Vt dependence. So, this is all about the mobility, effective mobility, what we have discussed in last lecture, but there are some additional effects which are called extrinsic effect we need to take care of when you model the MOS transistor. So, out of which let us discuss about the extrinsic source and drain resistance. To make it clear what is intrinsic and extrinsic, let me show you a cross section view of MOSFET. We said that this is my source, this is drain, you do have a oxide and a gate and body. Till now we have discussed about depletion charge, about inversion charge, about oxide charge and the gate charge, meaning we have discussed all about this, which is denoted by a dotted line. This box is in general called intrinsic part of the MOSFET. This intrinsic part of the MOSFET is only is the one who captures the operation of the MOSFET. However, the complete operation of the MOSFET is also governed by the extrinsic part. Now, what are those extrinsic part? You can see we do have source and it does have some resistance. Similarly, the drain have some resistance. Similarly, the gate have some resistance and other extra parasitic effects will come into picture. Those effects will limit the operation of MOSFET. So, you cannot say the MOSFET operation, the whole MOSFET operation is captured by this intrinsic part only. This extrinsic part needs to be taken care of, and it is very important when you model these devices for high frequency applications or small signal applications, right. In this analysis we only considered the resistances, the source resistance and the drain resistance. We are considering this analysis is completely DC so that the gate current is 0, and if the gate current is 0, there is no drop in the gate resistance, and hence Rg is not considered. So this schematic picture can be converted into a symbolic picture which shows that this black region or is your intrinsic part, this part is your intrinsic part, which is drain, this is source, and this is gate. As I mentioned, we are not considering the gate resistance because we are considering only the DC analysis at this stage. So there will be a drain resistance which can be denoted by Rd, and there will be a source resistance which can be denoted by Rs, correct, and there will be a current flows between the terminals which is drain terminal and source terminal. So the current will be flowing in this direction, which is IDS. So you see effectively the terminal to terminal voltage, which is VGS, is this, not this. It means the effective VGS, which is actually experienced by the intrinsic part, it is not VGS, it is VGS dash, or you can say VGS cap. Similarly, the effective VDS, which is experienced by the intrinsic part, it is VDS cap, not VDS, right? And hence if you simple solve a KVL, you can see that VGS is equals to VGS cap plus ID into Rs, or you can write IDS, right? Similarly, VDS, the overall VDS, this voltage, is equals to VDS cap plus IDS into Rs plus Rd, and hence you can see the drain current is also dependent on these resistances. So when you are modeling these resistances, or when you are modeling this MOSFET including the parasitic effects, then you need to include these resistance into account. So let us solve again for non-saturation condition, means IDSN. We are considering two approximations here. First, we are keeping VDS very low. It means it is positive, but it is very low, we are in non-saturation condition. The second is we are considering the drop across these resistance is very, very small, and hence we will only consider the linear terms, right? The higher order terms will be neglected. Higher order terms will be neglected. So with these two approximation, let us proceed to rewrite this equation of IDSN. So we can simply say IDSN is equals to W divided by L into mu into COX dash VGS minus VT into VDS minus alpha times of VDS whole square by 2. But make sure in this case my VGS is not VGS, it is VGS cap, because the VGS cap is the effective gate to source voltage and VDS cap is the effective drain to source voltage experienced by the intrinsic part of the MOSFET, and this current what we derived as IDSN, it is derived for intrinsic part. So we need to replace this VGS dash for the terminal voltage, which is nothing but W divided by L mu into COX dash into this VGS dash can be written as VGS minus RS into IDS minus VT, and there will be another term which is VDS minus IDS into Rs plus Rd minus alpha by 2 into VDS minus IDS into Rs plus Rd whole square, correct. For the simplification of this solution, we are considering few parameters as VGS minus VT you consider as A, VDS you consider as B, and you have another term Rs plus Rd you consider as RT. T stands for total. So rewrite this equation as W divided by L mu into COX dash VGS minus VT you can rewrite as A minus Rs into IDS into VDS is B minus IDS into RT minus alpha by 2 B minus IDS into RT whole square. Just solve further. W by L mu into COX dash into this will give you AB minus A into RT into IDS, right, minus B into RS into IDS plus B into, sorry, this will give you IDS square into RS into RT minus alpha by 2 B square minus alpha by 2 IDS square into RT square plus alpha IDS into RT into VDS or RT into B, correct. So, here we are ignoring these terms, as we have mentioned. We are solving this equation for some approximation. The first approximation is the drop across the resistance we are considering as to be very, very small, and we are ignoring the higher order term. And if you see here also, this is what RT, it means what, RS plus RD into VDS. VDS is very, very small, so we can simply ignore that term also. If you just simplify this equation, this term and this term have IDS component, you take it at left hand side, take IDS common. So, instead of N we can simply write IDS, which is for non saturation only. You will get 1 plus A into RT plus B into RS at the left hand side, and in right hand side you will left with W by mu into COX dash AB, this term, this is gone at left to left side cancel, and you left with alpha by 2 into B square, right. This term is also ignored because VDS is very small. So, the right hand side term is nothing but W by L mu into COX dash into A is what, VGS minus VT, and B is what, VDS minus alpha by 2 VDS square divided by 2, right. Now, in the right hand side you have a term which is 1 plus A into RT. So, I can rewrite as 1 plus A is VGS minus VT into RT plus B is VDS into RS. Again, for the sake of simplicity of this model, we are assuming that VDS is very, very small and you can ignore. So, you will get the overall current equation as W divided by L into mu into COX dash VGS minus VT into VDS minus VDS square into alpha by 2 divided by some term which comprises as 1 plus RT into VGS minus VT. I missed one term. When you make it at left hand side, this will be multiplied with W by L into mu into COX dash, right. So, here there will be a W by L into mu into COX dash terms will also come, because when you are making it at you are putting it to left hand side, W by L into mu into CX term will come, right. So, this equation can again rewrite as the above part is IDSN, but the below part is you can rewrite as 1 plus beta R into VGS minus VT, where beta is nothing but, or beta R is nothing but RT into W into mu COX dash divided by L, where RT is nothing but RS plus RD into mu into COX dash W divided by L here. So, the closed form equation of our current including the source drain resistance is given by IDSN divided by 1 plus beta R into VGS minus VT. If you see closely, this is same kind of equation what we have obtained when we were considering about the mobility effect, right. In that condition also the IDS was nothing but IDSN divided by 1 plus theta times of VGS minus VT. So this is just a coincidence that Vgs minus Vt term is coming in the denominator in both the equations. However, there is no linkage between the mobility effect and the source drain resistance. So it is incorrect to say that the mobility is degraded because of the source and drain resistances, though the equation remains same, but the statement, the physical meaning is different. That is what it is mentioned, that mobility degradation and series resistances effects are physically different phenomena. Now, what will happen if in this equation I will include the mobility effect? So instead of only mu, if I take mobility effect, then the overall current will be given as IDSN divided by 1 plus theta times of Vgs minus Vt. This term is coming because of mobility effect, and 1 plus beta r into Vgs minus Vt. This term is coming of source drain resistance. Considering again, to remove the higher order term, you can simply denote Vds as 1 plus theta plus beta r into Vgs minus Vt. This equation also says that when you include the mobility effect term as well as the extrinsic component, the current is no longer be valid as square root term, right, because IDS in the saturation was given by Vgs minus Vt whole square. However, because of this term, Vgs minus Vt is coming in the denominator and it is linearly dependent with Vgs minus Vt. Here it is to be noted here that for simplicity of TCAT simulations and modeling, we can simply ignore the series resistances. It means the gate resistance, source resistance and drain resistance. When you are going for high frequency application or high frequency modeling and small signal analysis, then you need to capture these effects. To avoid these effects of source and drain resistances, generally what we do, we wrap these source and drain resistances by the metal, for example titanium, tantalum, right, and they form a disilicides. The process of forming these disilicides is called salicide process or self-aligned silicide process. Because of this, the effective resistance of the source and drain will be reduced approximately 5 times or 10 times. So this is a way to reduce the source and drain resistances, which is yes a problematic or an extrinsic effect in MOS transistor modeling. Let us see the another effect which affects the performance of your MOSFET or in general semiconductor based devices. We can simply say the temperature is a very crucial parameter which actually captures all of your important parameter related to the semiconductor. For example, the well known parameters are intrinsic carrier concentration, right, Ni, intrinsic concentration. This is dependent on temperature. It is nothing but Ni is approximately equal to T to the power of 3 by 2. The second is the band gap, Eg. Eg is also dependent on temperature, right. With Virchowny's rule, we can find out how the temperature influences the band gap. Third is Fermi potential, phi f, which is given by kT divided by Q log of Na by Ni. This is also dependent on temperature, meaning the temperature is actually changing the basic property of the semiconductor, and hence it is very important parameter you need to take care of while modeling or simulating a particular device. As far as MOSFET is concerned, the important concern is all about mobility, because we have seen that mobility is captured by different scattering event, and when you increase the temperature or decrease the temperature, then these scattering event will be altered. For example, when you are at very low field and we said that Coulomb scattering will dominate, at that end experimental suggests that the mobility is increases, which means the mobility is actually given by T to the power of 3 by 2 divided by Ni, which is impurity scattering dominant mobility, right. Here if you increase the temperature, the mobility is increases. Yes, if you increase the impurity concentration, the mobility will decrease. However, when you go and increase the effective field, then you are in this range where the phonon scattering dominance, and because of the phonon scattering or the lattice scattering, the mobility is decreases by t to the power of minus 3 by 2. So, if we generally plot a graph of mobility versus temperature, so it is log mobility, you will get that the trend will look like this. The mobility is increases initially and then it will decreases. That is what we have seen in last lecture also. Now, the temperature basically captures the mobility event in terms of surface mobility as well. So, this equation is in general written for strong inversion model, where these are the parameters or the fitting parameters we need to get it. In addition to that, we have defined few more parameters like theta, theta b, beta r, right. These are related to the effective mobility equation. This is related to the extrinsic source resistance equation. These all are dependent on temperature. But in general, when you model these equations, these are considered as a fitting parameter because it is really hard to calculate and see the impact of temperature on these parameters. So, in simulation tools also you will find that these parameters are the fitting parameters you need to tune with to get a best fit in comparison to the experimental data. In addition, as I mentioned, the Fermi potential is dependent on temperature, which is kT by q log of Na by Ni, and if the Fermi potential is dependent on temperature, it directly affects your threshold voltage, right, which is obvious that if you increase the temperature, the threshold voltage will decrease because the charges will come up, charges will acquire higher energy and it will come early near the surface. That is what is given by here. The threshold voltage will decrease when you increase the temperature, where this Tr stands for room temperature, which is nothing but 300 Kelvin, and T is an absolute temperature at which you want to calculate particular threshold voltage or particular current in comparison with the room temperature, correct. The value of K4, which is a fitting parameter again, is nearly about 0.5 to 3 millivolt per Kelvin. Now, I can rearrange this equation and see how my temperature affects the current equation of MOSFET. So, in general, we have derived this equation as ID equals to 1 over 2 mu into W divided by L into COX dash into VGS minus VT square in saturation. So, I can simply say IDS dash, but I need to see the impact of temperature on threshold voltage and other parameters, or in general I need to see the impact of temperature in current. So, I can simply say it is square root of IDS half of W divided by L COX dash square root, and now this mobility is also a function of temperature. Similarly, this threshold voltage is also a function of temperature. So, in general I do have two parameters in my drain current equation which is dependent on temperature. Let us see what is the impact of these two parameters in plotting the current versus voltage characteristic. So, in the y axis we are taking square root of IDS and in x axis we are sweeping VGS. So, as we mentioned, let us consider this graph is for some temperature T1. So, till this point, till the inversion does not happen, the current is approximately 0 and then it will increases like this. It should increase linearly, but due to mobility effect it is a bit lower. So, we are not considering the mobility effect at this stage, we are only saying that how the temperature affects the current. So, this is the current corresponding to the temperature T1. Now, let us consider you increase the temperature T2, which means T2 is greater than T1. So, two effects will occur simultaneously. First thing is the threshold voltage reduces, that is what this curve shifted at this side, because this point will give you threshold voltage which is nothing but Vt plus alpha by 2 into Vds, right. So, the point will shifted to the left, threshold voltage is reduces as we have mentioned here. Now, the second is the mobility is also reduces. It means what? The current will increase like this, but the mobility which is actually encountered the drain current equation, right, the current equation or the current will reduce at this point. So, you are getting a decrease in the current. So, let us in a similar way, this is T3 where T3 is greater than T2 and you will get this kind of curve. While plotting this kind of curve, you will find that there is a zone where the graphs are interacting. This zone can be denoted as ZTC point or tip point. ZTC stands for zero temperature coefficient point, or tip in the sense temperature independent point, right. It means in this point the impact of temperature is negligible, and hence as a designer you need to operate the device in this region so that the effect of temperature is negligible. This is similar as the Q point in your BJT, where you decide which point I need to choose to operate my device. So in terms of temperature, I need to choose this ZTC point where I will operate the device, right. So let's see the impact of temperature also in terms of subthreshold slope, which is a very important parameter we have already discussed in weak inversion. The subthreshold slope was in general given by 2.3 into n times of phi t, where phi t is nothing but what? Thermal voltage kT by Q, and it is completely dependent on temperature. So when you reduce the temperature, then the subthreshold slope will increase. That is what it is visible here. If you reduce the temperature, the subthreshold slope, the slope of this log ID, right, versus VGS is increased, and the slope is deteriorated when you increase the temperature because of this factor. Now the next extrinsic effect we can think like a breakdown. When we are applying our voltages in our MOSFETs, for example, we do have source terminal, drain terminal, gate terminal and body terminal. You are applying some voltages to operate the MOSFET, but these voltages should have some limit. If you are applying, let us say, VDS, ultimately this VDS is making this junction n plus, this is P, this junction is nothing but similar as PN junction. So if you increase VDS, what will happen? The reverse voltage across this PN junction diode will increase. Because of increase in VDS, the carrier will move from source to drain, and because of this depletion region occur near the source, near the drain substrate junction or the source substrate junction. In this depletion region, these high energetic carriers are coming, they get accelerated and they cause impact ionization. Yeah. These high energy electrons will interact with this silicon atom and they causes electron hole pair. As this is connected to positive side, the electron will go this side. So the electron movement is towards the drain and the whole movement is towards the substrate. So this will give you drain to body current, correct. Because of that, the overall current of the IDS is increases. So in breakdown region, you are expecting the current will look like this, but it will somewhat increase. That is what it is visible here. This is breakdown phenomena. Because of high energy, because of high electric field, what happens is there is an impact ionization and avalanche occur. Because of avalanche phenomena, the current is increases and you can say a breakdown, right. This is called non-destructive breakdown. It means if you reduce down the voltage, ultimately the current will go down in the limited range. However, there are also destructive breakdowns. What happens is, in the MOSFET itself, if these high energy particles get enough energy to break the oxide, because this is connected to positive, right, and here you do have high energy electrons. So some of the electrons acquire so much energy that electrons are called hot electrons or hot carriers. These hot carrier will go through the silicon oxide and break down. That is what a destructive breakdown. That is mentioned here, that oxide breakdown is a destructive breakdown and it causes a permanent short circuit through the gate insulator, right, leading to a irreversible device failure. Similarly, the static charges which are building or buildup in the oxide, there also causes a destructive breakdown. So after this all phenomena, let me introduce a p channel transistor. In the previous lectures, we have discussed all about the n channel transistors. We have modeled the n channel transistor considering our gate is positive, substrate is n type, substrate is p type, you have n plus source, n plus drain, and you are applying positive voltages. In some aspect we have also discussed about forward and reverse saturation, but that is also meant for n type device or n channel transistor. However, we can also design a different type of transistor which is just opposite to the n channel transistor, which is nothing but a p channel transistor. In p channel transistor, the substrate or the body is made up of n type, the source and drain is made up of p type semiconductor, or it is p plus. Now the phenomena what we have discussed, like weak inversion, depletion, moderate inversion, strong inversion, everything will hold good, but here the polarity of the voltage will be reverse. So you need to apply a negative voltage. This negative voltage will causes the holes to pile up. So the inversion region comprises holes in the p channel devices, not the electrons, whereas in NMOS we consider that the electrons are coming near the surface and causes the inversion region. The current which flows between this is from source to drain, so ISD, because you are connecting a negative voltage here. This negative voltage will attract these holes and this give rise to a current which is in the direction of holes, right, because the holes are positive charges. Now all the parameters what we have defined, like body factor is same as in n channel MOSFET, but we need to use a flipped polarity. What it means is, in general we use the same equations what we derived for n channel MOSFETs. You can see that ID is nothing but W divided by L mu into Cox into VGS minus VT into VDS minus alpha by 2 VDS square, what we have derived for non-saturation condition for n channel MOSFET, non-saturation, right. However, it is important to note here, this current should flow from source to drain, but to get on the currents equation on the same page or having a similarity with n channel MOSFET, we are representing it to IDS, drain to source. If there will be a polarity of the current is changed, there will be a negative coming up. Similarly, if you write the threshold voltage equation, you will see that negative term coming here, because when you are applying a negative voltage at the gate, the surface potential will also be negative. That negative surface potential is causing the holes to pile up, and hence the value of negative or the negative sign is coming in terms of in front of your body factor, in terms of in front of your terminal voltages, etc. So I can simply say in a single statement that PMOS device can be considered as a polarity flipped NMOS transistor. I need to take utmost care when you are considering n channel MOSFET and p channel MOSFET on a same circuit. Then the polarity will be chosen wisely such that you are applying the terminal voltage to the respective transistors. Similarly, if I want to plot ID VD characteristic, so as I said that your VDS will be negative, so you cannot take here, you need to take VDS as negative, and if you are taking VDS negative, then you will get what, ISD. But to get the same equations on a same page in comparison to the n channel MOSFET, we are representing this, instead of ISD we are representing by IDS with a negative sign. So the current is negative, the voltage is negative, the curve will come up in third quadrant, that is what we are plotting in third quadrant. So this is IDS scale, so this will become minus IDS scale, this is VDS scale, so this will become minus VDS scale, and similarly, and with the same consideration that when you vary VGS, the current is increases and getting saturated. So this curve is same as n channel transistor, but with a flipped version, correct. Here we need to see that the mobility of holes is very less or approximately 3 times less to the n channel transistor, and hence the effect of current is also less. So, sometimes in simulation you need to include the area factor and all. We are not going in that aspect, but to maintain a constant current, let us say you are designing a CMOS inverter. To maintain a constant current, you need to include some area factor such that the mobility effect can be counterbalanced, right. Similar effect we can see the effect of VSB. If VSB is increased, the threshold voltage was increased, and hence the curve get shrinked. That is what we have already discussed when we were discussing about n channel transistor. Only thing you need to take care of is the polarity of the voltages and the current will flipped in PMOS transistor. So, let me summarize this lecture. In this lecture we have seen the extrinsic effects. In addition to the intrinsic MOS transistor, which we discussed by a dotted line, that this is the intrinsic part, there are some additional extrinsic part, or you can say parasitics, which limits the overall performance. Out of this we have considered a few, for example, source and drain resistance impact, and we derived an equation and we found that the overall current is restricted or is get altered because of this source drain resistance as IDS not including source drain resistance divided by 1 plus some beta r into VGS minus VT, right. We have also seen how the temperature affects your MOSFET operation in such a way that it affects the basic properties of semiconductor like intrinsic carrier concentration, Fermi potential, threshold voltage. In terms of MOSFETs, the temperature affects the mobility, the drain current, because the drain current is nothing but a function of mobility and threshold voltage. In addition, we have seen there will be a possibility of breakdown if you applied the voltages beyond some limit. Thus, you have to have some limited threshold voltage, limited voltage needs to be applied in your device. At last, we have seen the another flavor of MOS transistor, which is called PMOS transistor, where we can define in one statement that PMOS transistor is nothing but a polarity flipped transistor of NMOS device, where the polarities of terminal voltage and current get flipped, and all the inherent physics what we have discussed in terms of depletion, inversion, weak inversion, extra will be applicable for PMOS transistor similarly as what we have discussed in NMOS transistor. So, we will stop here for today. Until then, take care.